The question says that determine the effective focal length of the combination of the two lenses in exercise 9.10 if they are placed 8 centimeter apart with their principal axis coincident. Does the answer depend on which side of the combination a beam of parallel light is incident? Is the notion of effective focal length of this system useful at all? So, in the previous exercise of 9.10, we were given two lenses, a convex lens and a concave lens, and we were asked to find the F effective or the net focal length of the system. Now, in this question, it is asking that these two lenses are kept apart 8 centimeter. Now, we have to find out what would be the effective focal length, and does that hold any meaning at all? Here, we have to determine the effective focal length of the combination of the two lenses, and we also need to answer that will the effective focal length depend on which side of the lens the light is coming from, or which side of the lens the object is placed. And we also need to comment, is the notion of effective focal length of the system useful at all? Now, here we can make two cases to find out whether the answer will depend on which side of the combination of the beam of parallel light is incident. We will first put concave lens on the back side of the convex lens, or if we imagine the rays coming from an object that is placed at infinite, or the rays are parallel. So at first we will put the convex lens on the left hand side, and then in the second case we will put concave lens on the left hand side and see will the answer depend. Now for an object at infinity, on the left hand side the image will form at the focus of the convex lens. Since we have been given the focus of 30 centimeter, so the distance of image from for this lens would be v equals to 30 centimeter. As u1 is infinity, u1 as in the case of convex lens, that is the first lens, we can say that v1 is equals to 30 centimeter, and u2 here represents the object distance for the concave lens, that is the second lens. When this lens is forming the image, it would be 30 centimeter on the right hand side of the lens. So 30 centimeter from this direction would be somewhere here. Now the distance of this image which will act as an object for this concave lens will be 30 minus 8, that will be equal to 22 centimeter. So for this lens, the object will be placed at 22 centimeter on the right hand side. So we can write u2 as 22 centimeter. Now using the lens formula for this second lens, we can find out the value of its v, that is the image formation, the position of the image. So using this lens formula for this concave lens, we can write 1 by v equals to 1 by f plus 1 by u, and 1 by u is 1 by 22 centimeter, and 1 by f is 1 by minus of 20 centimeter, because the focal length is given as 20 centimeter, and since it is a concave lens we can write it as minus 20. So calculating this, we will get a value of v as minus 220 centimeter. So for this lens arrangement, we will get, when the object is at infinity, the final image will be forming at v equals to minus of 220 centimeter on the left hand side of this lens by a distance of minus of 220 centimeter. Now we will consider the second case in which concave lens is the first lens and the convex lens is the second lens. So here v1 would be equals to minus of f, because when the incident ray is there, it will virtually tend to form an image in front of the concave lens 20 centimeter or equals to its focal length. Now we can treat this image as a virtual object for this convex lens. So u2 would be equal to this 20 centimeter plus of this 8 centimeter distance. So the total value of u2 would be minus of 28 centimeter with sign convention. So again applying lens formula over here. So we will get 1 by v equals to 1 by f plus 1 by u, and we saw that 1 by u is equals to 1 by minus of 28 centimeter, and since focal length is positive for the convex lens, so it will be 1 by 30. Calculating this, we will get a value of v as minus of 420 centimeter. Now we can comment that seeing this results that v changed from the previous case of 220 centimeters, so that we can say that yes, the answer depend on which side the incident ray is coming from, because v has changed or the final image distance has changed. And we can also comment that no, the notion of effective focal length won't work in this case, because there can't be f effective, as the image position is varying depending upon which side or the which lens is receiving the first incident rays. Now the second question asked, like, an object of 1.5 centimeter is placed on the side of the convex lens in arrangement A above. The distance between the object and the convex lens is 40 centimeter. Determine the magnification produced by the two lens system and the size of the image. So now using this arrangement, we have been given the value of u, that is the object distance from the convex lens, and that is of 40 centimeter, and the object size or the height of object is given, that is 1.5 centimeter, and we have to find out what is the magnification produced by the two lens system, and also we have to determine the size of the image. So let's go to the calculation. So this is the arrangement that we were talking about. The object is placed in front of convex lens and u has been given, and that is a value of minus of 40 centimeter. Focal length of this convex lens is 30 centimeter, and focal length of this concave lens is minus 20 centimeter, and the distance between these two lenses is again 8 centimeter. So we will consider this first lens and this as the second lens. So u1 would be equal to minus of 40 centimeter with the sign convention. So using lens formula for finding out the image produced by this convex lens, so 1 by v equal to minus of 1 by u, and that is u is minus of 40. So 1 by v equals to minus of 1 by 40, and that would equal to focal length. Focal length of convex lens is positive, so it will be equal to 1 of 1 by 30. So calculating here v, we will get a value of 120 centimeter. Now we can see that from the pole of this lens, the first image will form 1 centimeter on the right hand side of this lens. So this image will act as an object for this concave lens. So we can find out the object distance for this concave lens, and that would be equal to u2 would be equal to this 120 centimeter minus of this distance 8 centimeter, and that will come out to be equal to 112 centimeter. Since this distance is on the right hand side of the concave lens, so it is going to be positive, or u2 is going to be plus of 112 centimeter. Now applying the lens law over here, 1 by v minus 1 by equals to 1 by f. Here f is negative because it is a concave lens, and 1 by v minus 1 by 112 would be equal to minus of 1 by 20. So solving this for v, we will get a value of v as minus of 560 by 23 centimeter. That is, the position of image is on the left hand side of this concave lens at minus of 560 by 23 centimeter on the left hand side of this concave lens. So we have got this value of u1, v1 and u1, and v2 and u2. Now we can find out the magnification of each lens independently, and then we can find out the product of magnification so that we can get the net magnification. So magnification for the convex lens would be equal to m1 equals to 120 by minus of 40, as m is equals to v upon u. So we can divide it and get the value of magnification by the first lens as minus of 3, and by second lens similarly we will substitute the values in this formula, and we will get the value of minus of 5 by 23. Now net magnification will be equal to the product of these two independent magnifications, and that will be equal to 0.652. That is, the net magnification is less than 1 and it is diminished in size. So the final height of this image is going to be equal to net magnification multiplied by the original height, and that we will get solution as 0.98 centimeter, because the initial height was 1.5 centimeter. So we can multiply it with 0.652. That is a net magnification, and we will get the value as 0.98 centimeter. Thank you.